Welcome back, Algebra 2 students. Today we're going to cover lesson 5-6 on inverse relations and functions. So in our first example, we're asked to represent the inverse of a relation. So what is the inverse of the relation represented in the table? So first of all, if you remember, a relation is just a set of ordered pairs, which is what we have here in this table. The inverse, to get an inverse of a relation, we interchange the x and y coordinates. So what was an x coordinate becomes a y coordinate, and what was a y coordinate becomes the x coordinate. So that would look like this. Okay, here's the original relation. And then notice how what was the y column becomes the x column, what was the x column becomes the y column. So again, we're switching those values for x and y. Now, over here, this blurb says that the relation is a function, and it is. And the easiest way to test for that is by looking at the x values. Okay. Over here in this box, it says if two distinct values in the domain of f have the same image, when they say image, they mean y value, then the inverse of f is not a function. So if we look at the domain, if all of the domain elements are different, it's automatically a function. When we look at the inverse, we've got two x values that are 1s, and they go to different y values. So we have 1, -2, and we have 1, 1. Therefore, this inverse relation is not a function. So let's try the try it. We're going to identify the inverse relation and then determine if it is a function or not. Okay, so go ahead and try this. Set up the table by interchanging the x and y values. Okay, I'm going to do it as well. So what was a y value becomes an x. So my first coordinate would have an x value of 9 and a y value of -1. Then I'm going to have 7 and 0. And then 5 and 1. 3 and 2. Let's see, 1 and 3 and -1 and 4. So I'm going to just check real quick. My x row should match what was my y row, and it does. And my y row should match what was the original x row, and it does. Okay, so there's all my new coordinates. Now also notice this notation. That's not a power, that's the universal symbol for inverse. Okay, so when you see that y to the -1, that means you'd read this as y inverse. Okay. So is this a function? If we look at all of the x values, again, all of the domain elements are different. So if they're different, then the answer is yes. Okay, it's automatically a function because there's no repeated domain elements. Okay, I threw in one additional example. So you go ahead and try this one, fill in the chart, and then determine if it's a relation, if the relation is a function, if the inverse relation is a function. So pause the video, come back when you're done. Okay, let's see. So hopefully your chart looks like this. The x value of 2, we have 2 of them. One goes to -1, one goes to 6. So the inverse is not a function. Okay. So example 2. Now we're going to find the equation of an inverse. So we're going to talk about, there's a few steps involved in this process. So step 1, we replace the f of x notation with y. So we're going to change this from f of x equal to x squared to y equal to x squared. Step 2 is to switch x and y. Just like we did in the chart, you do the same thing within an equation. So it becomes x is equal to y squared. And then our last step is to solve for y. So when we take the root, we get y is equal to, this is where the plus or minus comes in, plus or minus root x. So the inverse of f can be represented algebraically by the equation y is equal to plus or minus root x. Now if we went back to function notation, that would look like this. So when you see this, again, this is not an exponent, you would read this as f inverse of x. So f inverse of x is plus or minus root x. Part B, how are the graphs of y equal to x squared and y equal to plus or minus root x related? So here in blue, there's our parabola for x squared. And then the y equal to plus or minus root x, remember root x looked like this. It starts at the origin and increases to the right. So the negative of it would be the reflection over the x-axis, which gives you this piece of it. So it's actually a parabola opening to the right. Okay, so the graph of the inverse of f is the reflection of the graph y equals x squared across the line y equals x. So that's that green line here. If you look at the two graphs, do you see the symmetry over the line? In other words, if we took the blue graph of x squared and we reflected it over the line y equals x, we would get the graph of the inverse. And that will always be the case between a function and its inverse. You'll see that symmetry over the line y equals x. So this says the range of f is y greater than or equal to 0, so the domain of the inverse is x greater than or equal to 0. So domain and range interchange for all of these inverses. The inverse is not a function. Now here's another important thing. The way you can test with the graph is by a vertical line test. If the graph passes the vertical line test, meaning anywhere along the graph, if I draw a vertical line and I go through only one point, then the graph represents the graph of a function. Okay, so if you look at x squared, no matter where I draw a vertical line along that graph, I'm only ever going to go through one point. So the graph of x squared is a function. If I look at the inverse, there's lots of places where if I draw a vertical line, I'm going to go through 2 points. That means it fails the test, so the inverse is not a function. So that's a really nice way, if you have the graph, to determine whether or not something is a function, okay, whether if it passes that vertical line test or not. Okay, so find an equation of an inverse relation. So here we have f of x equal to 2x plus 1. We're asked to write an equation to represent the inverse of f. So I'm going to work through this one with you. We're going to start off by replacing the f of x with a y. So it's y equal to 2x plus 1. Step 2, we interchange the x and y. So we're going to replace y with x and replace x with y. And then our last step is to solve for y. So I'm going to subtract the 1, and that equals 2y. And then my last step is to divide by 2, so that would give me 1/2 x minus 1/2. So there's my equation. Okay, notice that the graph of f of x is 2x plus 1. That's a line, right? This is also a line. This is a line with a y-intercept of 1, a slope of 2. Here our y-intercept is negative 1/2. The slope is a 1/2. Okay, so we should be able to picture what these lines look like. neither one of them is a vertical line, so both of these lines would pass that vertical line test. So how can you use the graph of f to determine if the inverse of f is a function? And explain your answer. So when they say use the graph of f, there's another line test that we can use. If I have, let's say that's our 2x plus 1. We can also do what we call the horizontal line test. If the original function passes the horizontal line test, then its inverse is automatically a function. Because if we go back to this picture, notice here how x squared, that would fail horizontal line test. If I draw a horizontal line, I'm going to go through 2 points, right, on x squared. That means that the inverse would fail the vertical line test, which it does. So we can test the original graph using the horizontal line to determine whether if its inverse is a function or not. So any graph that fails the horizontal line test, its inverse is not a function. So going back to this example, this line passes both tests, right? Any line other than a vertical would pass the test. So because it does, its inverse is not a function. I'm sorry, did I say that backwards? Any line other than verticals would pass the vertical line test. Any line other than a horizontal would pass the horizontal line test. Therefore, the inverses are functions. Okay, so let's see. Now we have a cube root. We follow the same steps. We're going to come up with the inverse of f. So we're going to start off by replacing f of x with y. And then we're going to, let's see, we have a choice. We could divide by the negative or cube both sides. So why don't we take care of the negative first? Oh, sorry. First we have to exchange variables. So let's make this x is equal to negative cube root 4y. Now we'll divide by the negative. This negative x is equal to the cube root of 4y. And now I'm going to cube both sides. Okay, so cubing this, it stays negative. I have negative x cubed. And on this side, cubing undoes the cube root. So I have 4y. And then dividing by 4, I get negative x cubed over 4 is equal to y. Or, if you wanted to make it a negative 1/4, x cubed is equal to y. You could write it this way with the fraction separated from the x cubed. Okay, so here's the try it. So for this one, you're asked to sketch the graph of f, which is 2 minus cube root of x minus 1. Okay, think about your transformations. You've got 3 things going on here. Or that plus 1, that would make the graph shift which way? Hopefully you said to the left, right? So it's going to go left 1 unit. This 2, that's our vertical shift. It's a positive 2, so it's going to shift upward. Okay, and then there's a negative here, so that's also going to cause a reflection. Over which axis? Hopefully you said x-axis. So the order would be, we're going to shift to the left, reflect over the axis, and then the last thing is the vertical shift. So go ahead and sketch the graph, then verify the inverse that will be a function, and write the equation of the inverse. So pause the video, go ahead and try that, come back when you're done, and we'll compare solutions. Okay, so here's the sketch of the graph. Okay, hopefully yours looks like that. Now they say verify that the inverse will be a function. So again, if we look at the horizontal line test, there is nowhere along this graph that when I draw a horizontal line, it's going to go through more than one point. And eventually it appears as though the graph is leveling off, but remember, it never really does. Our domain is all reals, our range is all reals, so it's going to keep on traveling left and right. It's going to keep traveling upward and downward. So it passes the horizontal line test, which means its inverse is a function. And here is that function. So hopefully you got 2 minus x cubed minus 1. So let's see. We'll go through the steps here. I'm going to write it out as x is equal to 2 minus cube root of y plus 1. I'm going to subtract the subtract the 2. I have a negative in front of that cube root. So if I divide by the negative, that's going to switch these signs. So I'll write it as 2 minus x. Then I'm going to cube both sides. Cubing this side undoes the cube root, so I have y plus 1. So my last step is to subtract 1, and that gives me 2 minus x quantity cubed minus 1. Okay, example 5, use composition to verify inverse functions. So what is the inverse of this, and how can you verify this? So let's first find the inverse. So we'll start off with x equaling 2y plus 5. Then I subtract the 5. And my last step is to divide by 2. And this time I'm just going to leave the whole thing over 2. Okay. Now, how can we verify this? Well, if f of g, remember our compositions from the last section, if f of g of x is equal to x and g of f of x is equal to x, then f and g are inverses. Okay, so we can verify it by calculating the composition f of g and g of f and seeing what happens. Okay, so to verify this, I'm going to find f of g, oops, and you can use either notation for the composition. This will be our g function. Okay, and here's our f function. So for f of g of x, I'm starting with f, so it's 2 times something plus 5. That something is the g function, so I'm plugging in x minus 5 over 2. Think of this 2 out front as 2 over 1. The 2's reduce out, and I'm left with x minus 5 plus 5, which gives me x. Now, I'm not done. I also, because this is an and, I have to verify g of f. So now I'm starting with the g function. So that's something minus 5 all over 2. What goes inside the parentheses is the f function. So I'm going to plug the 2x minus 5 in there. And then I can drop the parentheses. So it's 2x minus, oh, that was a plus 5, sorry. So it's 2x plus 5 minus 5. So the 5's cancel each other out. And I'm left with 2x over 2, which reduces to x. So since in both cases f of g of x equaled x and g of f of x equaled x, Therefore, f and g are inverses. Okay, so example 5, are the two functions x squared plus 5 and root x minus 5 inverses of each other? Okay, if we look at f of g, we're plugging root x minus 5 into x squared plus 5. So that's what this looks like. When we square this binomial, remember we get 3 terms. These first 3 terms is the square of root x minus 5. We can combine the 25 and the 5 and we get 30, but this, since it does not equal x, that's it, you're done. There's no reason to go on to check g of f. So if you find f of g of x is not equal to x, then you automatically know that they are not inverses. So example 5, try it. We've got A and B, so go ahead and try both of these. Use compositions to determine whether if f and g are inverses. So calculate both f of g and g of f if necessary. If f of g does not equal x, then you're done. If it does, then you do need to also find g of f to verify that they are inverses. So go ahead and try that, pause the video, come back when you're done, and we'll compare solutions. Okay, for letter A, hopefully you found that they are not inverses, because when you plug g inside f, that 1/4 times this -7 gives us a -7/4. That when added with the 7, that they don't cancel each other out. We don't get 0, so it's not equal to x, which means you're done. They are not inverses. For letter B, when we do f of g, we're plugging x cubed plus 1 inside cube root of x minus 1. So x cubed plus 1 minus 1 gives us x cubed. The cube root of that is x, so we do get x. So we need to go on and also verify g of f. So if we plug cube root of x minus 1 into x cubed plus 1, again, the cube and the cube root undo each other. We get x minus 1 plus 1. The 1's cancel each other out, and we get x. So f and g in this case are inverses. Okay, so the concept summary for this section. When you have inverse functions, remember to find the inverse of a function. We exchange the roles of the independent and dependent variables, right? Our x's and y's. So what was an x becomes a y. What was a y becomes an x. Same thing for equations. We interchange those variables and then solve for y. If you're looking at the graphs, remember you should see that symmetry across the line y is equal to x. Always, if you have inverses, you'll always see that symmetry. And then we can verify that two functions are inverses by using compositions. So here notice they replaced g with f inverse, so f of f inverse of x will equal x, and f inverse of f of x will equal x. So I hope you enjoyed this lesson. You can check the assignment table to see what your assignment is for today, and then submit it through the assignments block. Okay, so have a good day, and I'll see you next time.